Hello, and thank you for joining us tonight's USGS Public Lecture. We are happy you've taken an interest in USGS science. My name is Mitch, and I will be your host and moderator today. I have some quick announcements to make before I introduce our speaker. Next month's public lecture will be on February 23rd at 6 p.m. The speaker will be Kimberly Miller, USGS National Wildlife Health Center, and her talk will be Behind the Headlines of a Wildlife Disease Die-Off, the how and why of wildlife disease investigation. If you are watching this from a desktop computer and need to turn on closed captioning, please look at the bottom right-hand corner of the screen for the closed caption icon. It's the one with the two small C's. You can also use stream text for captioning. You can see the stream text link is provided in the Q&A window. To access the question and answer panel, you can click on the question mark icon in the upper right-hand corner of the screen. At the end of the lecture, we will have a Q&A session, and this panel is where you can submit your questions for our speaker. And now it's time to introduce you to our speaker. Joining us tonight is Charlie Mandeville. He has served as a program coordinator for the USGS Volcano Hazard Program, VHP, at USGS headquarters in Reston, Virginia, since September 2012. He was trained as a physical volcanologist and geochemist and has conducted research at volcanoes in Indonesia, Washington, Oregon, and Alaska. His PhD research focused on all aspects of the Krakatoa 1883 eruption in Indonesia and constituted the first integrated study of both onshore and offshore submarine samples from that eruption. He has managed the USGS Volcano Hazard Program, VHP, that operates volcano observatories in Hawaii, Alaska, Cascadia, California, and Yellowstone, and the Volcano Disaster Assistance Program in partnership with the U.S. Agency for International Development. He has coordinated USGS volcano monitoring with the efforts of cooperative universities and state geologic survey partners. He has represented the USGS VHP on interagency and international committees and meetings and has advocated the importance of a national volcano monitoring program to members of Congress as program coordinator of VHP. Without further ado, I'm going to pass it over to Charlie.
Thank you, Mitch, and it's wonderful to be here. And thank you for the opportunity to tell you this evening about what the Volcano Hazards Program is going to be up to in the next 5 to 6 years. I'm going to share my screen, and we can get that going. And on the screen now, you should see what is the cover to our Volcano Hazards Program Strategic Science Plan, which was published as a USGS circular in April of 2022. Shown in this picture is Mount Baker, a high-threat volcano, very high-threat volcano in Washington State that is currently under-monitored by what we refer to as National Volcano Early Warning System standards that we seek to implement over the next 5 to 6 years. Shown also in the foreground is the city of Bellingham, Washington. And because of volcanoes' proximity to air routes and also critical infrastructure and population centers, we have to make sure that volcanoes are adequately monitored in the US. And so I'll go to the next slide. The mission of the USGS Volcano Hazards Program is to enhance public safety and minimize social and economic disruption from eruptions through delivery of effective forecasts, warnings, and information on what volcano hazards may exist. And that depends on our understanding of volcanic processes. Here's the volcano observatories and their areas of jurisdiction, with the volcanoes showing up as triangles, color-coded according to their threat levels. Many of you may not know that there are 161 active volcanoes in the US, and we're one of the most volcanically active countries on Earth. Out of our 161 active and potentially active volcanoes, 18 are very high threat, 39 are high threat, 49 are moderate threat, 34 are low threat, and 21 are very low threat. And their threat ranking depends on things like exposure of people and property and critical infrastructure, as well as volcano threat. What is the nature of the hazards that the volcano has exhibited in past eruptions? And then what are the exposures of critical infrastructure, population, and heavily traveled air routes above that volcano? And the distribution of the volcanoes in the US according to states is shown on the right. Volcanic hazards can be broken down into a number of categories, those that are largely ground-based hazards, as well as the hazards that appear in the air. And the air, including the eruption clouds and the tephra fall, or the ash fall, as well as acid rain, and things like fog, can be felt many tens of kilometers to even hundreds and thousands of kilometers downwind. In addition to the airborne hazards, we also have what are referred to as ground-based hazards to contend with when volcanoes erupt. And those include things like pyroclastic density currents or pyroclastic flows and surges, things like volcanic mud flows or lahars, as well as things like lava flows. And can also have hydrothermal explosions. That happens when groundwater gets flashed to steam very violently because it comes into contact with magma. And we can have landslides that occur on volcanoes, sometimes during an eruption, but other times independent of any eruptive activity. So because of the nature of all of these hazards, as well as crumbling lava domes, we need to have a number of sensors on the volcano to warn the public and the emergency responders about hazards that might be imminent. Fortunately, volcanoes do things before they erupt, but to detect these eruption precursors, which typically show up weeks to months before an eruption, you can be activated quickly. Some of these can show up hours to days before an eruption. And these precursors include things like volcano deformation. The volcano literally inflates before it erupts. They deflate during eruption. You can have changes in the snow or ice cover on a volcano's summit. You'll also see typically increased seismicity, the number of small earthquakes or intermediate earthquakes occurring in and around the volcano's summit. You might also have changes in volcanic gas emission, or you may see anomalous high temperature pixels in thermal infrared remote sensing imagery from satellites. And if you've got changes in groundwater chemistry and stream geochemistry, you might detect those if you're doing regular sampling of those waters. The important point I want to make is ground-based instrumentation is crucial for the detection of unrest at volcanoes at the earliest stages, and the USGS uses all the data available, including satellite remote sensing. Part of the aim of the National Volcano Early Warning System is to assure that all volcanoes in the US are monitored at levels matching their threat. Enactment of the John Dingell Jr. Conservation Management and Recreation Act in March of 2019 authorized the USGS to establish this National Volcano Early Warning System. And how dangerous a volcano is depends on its past eruptive history, its proximity to population and infrastructure, and how well monitored it is depends on the array of instruments that are employed on it, typically within 25 kilometers of its summit. Shown here is Mount Rainier, a very high threat volcano in Washington state, which has erupted several times in the last 11,000 years. It's also given rise to volcanic mud flows that have reached Puget Sound and certainly have reached Orting and the outskirts of Tacoma, Washington. So therefore, it needs to be adequately monitored. It's also a very large volcano, over 14,000 feet. The National Volcano Early Warning System components will be that most of the USGS volcanoes in the nation are going to be proactively monitored at levels commensurate with the threats they pose. And all of our volcano observatories will be an interoperable system. We've also, of the past 6 months, have developed what we are now referring to as a National Volcano Information Service. So this will take the place of these two components known as the Volcano Watch Office and the National Volcano Data Center. And we also intend to have an external grants program that we can solicit proposals for amongst the greater academic and state survey community to advance volcano science in the U.S. We'll also, in the next several months, be establishing an interagency advisory committee, and this will be a federal advisory committee, namely with the agencies such as the Department of Transportation, the FAA, NOAA, FEMA, NASA, NSF, as well as the National Park Service, Bureau of Land Management, U.S. Forest Service, and U.S. Fish and Wildlife. Well, improvements to our volcano monitoring networks are going to be done through upgrading existing networks on monitored volcanoes. So in some cases, we're not starting from scratch. But in some areas, we'll be installing new networks on what have largely been unmonitored volcanoes. And we'll also be employing a greater variety of instruments on networks that already exist. Namely, we'll be putting gas sensors and visible and IR cameras and infrasound arrays, as well as INSAR corner reflectors into a network when and where applicable. Shown here are some recent network upgrades at Pulik Volcano in Alaska, at Boguslav Volcano, and at Mount Rainier. The U.S. volcanoes observatories under NVEWS will also become a much more integrated system with increased interoperability, standardization of analytical software, and more importantly, the capability to surge staff from one observatory to the next to deal with a volcanic crisis when that observatory goes into 24/7 response mode. The National Volcano Information Service will have redundant data paths to real-time data and near real-time data streams, such that even remote observatories can assist the observatory under emergency response with off-hours checks of data and analysis. And then we'll also be establishing that external grants program to advance volcano science and monitoring technologies in the future. We're not starting from scratch in that the USGS has already invested heavily in volcano monitoring infrastructure, firstly through the American Recovery and Reinvestment Act of 2009 to 2010, but also in 2018 when we did an update of the national volcano threat levels, as well as in 2018 when the program received one-time infrastructure funds of about $14.5 million to convert analog to digital stations in Alaska to new digital telemetered stations with digital broadband seismometers, as well as we've been replacing over the past 5 years an aging lahar detection system at Mount Rainier that was at the end of its service life, and now that's being replaced by a new system which will be in all major drainages of Mount Rainier. So over the next 5 years, we'll be strategically filling severe monitoring gaps on very high threat and high threat volcanoes. And in addition, we'll be developing cooperative agreements with state and university partners that we need to assist us in this endeavor. We've also, in 2018, published a new update to the volcano threat levels based on data that has come in since 2005 through 2018 to update the threat levels as needed. And this needs to be a living list that we reevaluate every 5 to 7 years. And this assessment will be used to help and guide and prioritize our volcano research, our hazard assessments, the emergency response plans that we develop with land managers and local governments and local civil defense. If we look at the distribution of the volcanoes according to threat level, 18 are very high threat. A lot of those are in Alaska. Some are in the Cascades of Washington and Northern California and Oregon. Others are located on the Big Island of Hawaii, and we'll, of course, be prioritizing our network modernization to the very high threat and high threat volcanoes during the first implementation phase of NVEWS. The law that establishes and authorizes the USGS to build this National Volcano Early Warning System will also be advised by high-level representatives from the Department of Transportation, the Federal Aviation Administration, the National Oceanic and Atmospheric Administration, the Administrator of the Federal Emergency Management Agency and Department of Homeland Security, members of the volcano science community, science agencies like NASA and NSF, but also the land managing agencies like the National Park Service, the U.S. Forest Service, the U.S. Fish and Wildlife Service, and BLM, and the private sector. So that committee establishment is currently underway. We hope to have their first meeting within calendar year 2023. There's also a need for adequate volcano monitoring in the U.S. and its territories, particularly those around the Pacific Basin. There are over 1,500 active volcanoes on Earth. 950 of these surround the Pacific Ocean. And on any given day, around the Pacific Rim, you might have as many as 61,300 persons traveling over North Pacific air routes daily. And this is National Transportation and Safety Board data that I'm quoting here. And also, if you drew a polygon from, say, Vancouver, British Columbia to San Diego, there are on the order of 770,000 persons traveling over the west coast of North America and British Columbia on a daily basis. And ash and jet engines don't mix, and even volcanoes that may seem remote need to be monitored at adequate levels because of their underlying of heavily trafficked air routes. So our first congressional authorization of NVEWS is not an appropriation, but it is a strong shot in the arm to the USGS for establishing this monitoring network, which improves our existing infrastructure. And we'll also be adding a variety of instruments, in many cases, to what were originally mostly seismic networks. So those new instruments might include GPS instruments. They might include visible and IR cameras. They might include new gas sensors, which can show up in a couple of forms, either SO2 cameras or scanning direct optical absorption spectrometers, or another instrument that we refer to as a multigas, which can be stationed permanently on the volcano, or they can actually be flown on UAS platforms. The importance of having this instrumentation in place on the volcano before unrest begins is it provides us lead time with which to issue warnings and forecasts. And in most cases, volcanoes typically show precursors before eruption that happen on the order of, days to weeks before eruption, and sometimes many months before an eruption. And here are some real life examples from recent eruptions. But the important point I want to make here is that you have to have the in-ground instrumentation on the volcano before unrest begins. You don't want to be playing catch up to a dangerous volcano that's escalating towards a hazardous eruption. We also look, every time we have the opportunity to improve a network on a volcano, we learn something. And a big part of adequate volcano forecasting is to learn to background fingerprint what the volcano does in its restive mode. Each time we improve the network on a volcano, we learn something new about what that volcano typically does. And in this slide here, I'm going to explain to you that in the period of 1980 to 2011, when we only had a couple of instruments on Newberry Volcano in Oregon, a very high threat volcano, we used to record about 10 earthquakes within 10 kilometers of the summit. And this volcano's most recent eruption was about 1,300 years ago. During the ARA stimulus funds, we put a new network of 8 co-located seismometers and GPS instruments on Newberry Volcano. And at the time that network was completed in 2011, we recorded 189 earthquakes. 160 of them were within 10 kilometers of Newberry summit. So the new network gives us a much better idea of what this volcano does in its background restive state, and we'll be able to see departures from that restive state much better in the future. So a large part and what we'll be doing over the years 2023 through 2027 at the Cascades Volcano Observatory, we'll be putting new instruments on Glacier Peak, Mount Adams, Mount Baker, and Mount Rainier. Lahar detection system will likely be completed. In Alaska, we'll be adding and improving networks at Okmok Volcano. We'll be putting stations west of Augustine Volcano in Cook Inlet. We'll be improving the monitoring systems at Macushan and Akutan. We'll be installing monitoring at Mount Edgecombe, which has erupted, shown volcanic unrest recently, and we want to get a network in place there. And we'll improve monitoring at Churchill, Kaguyak, Segwam, Vezvidov, and others. In California, we'll be turning our attention to the Mono Inyo Craters chain of volcanoes. We'll be adding earthquake early warning stations and broadband seismometers, but also co-located GPS stations for adequate coverage and continuous multi-gas and web cameras. In Hawaii, on the Big Island, we'll be improving monitoring networks at Kilauea and Mauna Loa, and also at Hualalai with 8 new broadband seismometers, a new infrasound array, some GNS sites, and 3 new tilt meters. And at Yellowstone, we'll be installing a new hydrothermal explosion monitoring station at the Norris Geyser Basin. And we'll be working with our University of Utah partner on conversion of analog to digital conversions of some of the seismic stations at Yellowstone. In the past 10 years, there's also been a revolution in the types of gas emission instrumentation we can place on volcanoes. Namely, we've developed internally at the USGS some new UV cameras for SO2 emission. We've also developed a multi-gas spectrometer, which can pretty much measure all the volcanic gases emitted, as well as some direct optical absorption scanner networks that makes real-time measurements of gas flux at volcanoes a reality. And shown here is a picture of Martin Damore performing some maintenance on a DOAS scanner installed at Turrialba. And we have similar capabilities here in the US. And shown on the right is a new multi-gas sensor installed at the summit of Augustine Volcano at Cook Inlet in Alaska in 2015. And these can even be flown on UAS platforms now. We've also learned during the 2018 eruption of Kilauea in Hawaii, the 1,001 uses of UAS platforms. And these were used to detect changes in topography at Kilauea's summit during caldera formation. They were also integrated with our multi-gas sensors for measurements of volcanic gas emission from the fissures that opened up during the 2018 Kilauea eruption, and also used to measure lava flow velocities from hovering above the lava flow, patrolling along the lava levees for signs of new breakouts and new flow fronts, as well as measuring the level of lava in some of the lava lakes at Kilauea's summit crater, as well as Pu'o'o crater, somewhat down rift in the Eastern Rift Valley. The other thing we had to deal with during the 2018 eruption of Kilauea is we had activity occurring both downslope in the lower East Rift Zone, as well as at Kilauea's summit, and this was happening simultaneously. And having UAS platforms available made observations and situational awareness easier for the USGS. Plus, we also had live video capability to broadcast into the HVO Observatory, as well as the State Office of Emergency Operations and Hawaii Civil Defense. And so we generated maps of likely lava flow paths, as well as keeping track of where new fissures were erupting. And some of these were originating in housing developments in Leilani Estates and Lanapuni Garden District. And despite the fact that over 724 homes were destroyed during the Kilauea 2018 eruption, there were no fatalities. And part of that was arisen from the capability to have both helicopter and UAS continuous situational awareness of what the lava flows were doing, as well as what the activity at Kilauea's summit happened to be. We also had assistance from the National Civil Applications Center and remote sensing from interferometric synthetic aperture radar that allowed us to keep track of lava flow fronts from satellite-based imagery, and these were shared not only amongst the Hawaiian Volcano Observatory, but also with civil defense and state emergency operations. Synthetic aperture radar is a very important tool for volcanology. Here's a shot from Mount Sinabung in Indonesia, which was erupting in 2014 and 2015. And it's an all-weather tool. In many cases, when the volcano's summit is obscured by clouds, the synthetic aperture radar can see right through the clouds and tell us what's happening on the volcano, particularly as lava flow fronts might be steepening and posing a hazard to villages and citizens downslope from the volcano's summit. The synthetic aperture radar satellites also tell us when a volcano may begin swelling as a result of being recharged from below from deeper magma sources. Here's a case from Mount Pulik in Alaska, where the deformation shown by INSAR, interferometric synthetic aperture radar, was showing inflation on the scale of about 24 centimeters during 1996 to 1998. And this appeared ahead of the seismic swarms which were recorded in May of 1998. So the synthetic aperture radar is very, very useful for telling us which volcanoes are being reactivated, sometimes before even the seismic activity begins to escalate. In 2021 and 2022, for much of the improvements of the volcano monitoring networks in Alaska, we required shipborne and helicopter logistics to support that work because you can't drive to these volcanoes. And we had initially on the order of about 180 analog stations to convert to new digital stations with digital telemetry. And we finally completed that work in 2022. In July of 2022, we replaced our last analog station in Alaska. And this is really important in an NVEWS sense because the new analog, the new digital telemetry has sufficient bandwidth to accommodate the other kind of instruments that we'd like to put on some of the volcanoes in Alaska to give us the greatest potential to see eruption precursors at the earliest stages in no matter what shape or form they appear in. With respect to the new lahar detection system at Mount Rainier in Washington, we've started putting new instruments in both the Carbon and Puyallup River drainages, starting in earnest in about 2017. In 2019, several new stations were added. In 2020, permits for 12 stations were granted. In 2021, 9 stations were installed. And in 2022, 8 new stations were installed and 2 were upgraded. And the last drainages will be instrumented probably this year in 2023 with expected completion by October of 2024. So in the next decade, we'll continue to invest in the National Volcano Early Warning System with emphasis on the very high and high threat volcanoes. We'll expand the use of satellite-based remote sensing for volcano monitoring, including the NISAR mission from NASA and the Indian Space Research Organization that will launch in January of 2024, and we'll have collection over our volcanoes every 16 days. We'll also be improving the forecasts and assessments of our volcanic systems and hazards, and we'll actually be improving mitigation of volcanic ash and gas hazards, both domestically in the United States, but also in close coordination and collaboration with our NOAA National Weather Service partner. And we'll develop improved portfolios of volcanic hazard products as digital portfolios with timely delivery to our end user partners. There's a new role for the National Weather Service and NOAA in that Congress recently passed the Volcanic Ash and Fumes Act in 2022 as part of the defense authorization. And that brings NOAA into a more formal volcano monitoring role, particularly with respect to volcanic smog, or what we refer to as VOG, and gas hazards. And we already do research with our NOAA colleagues on a number of volcano topics, but this will enable better monitoring capabilities and leveraging of resources in the future. And one thing that is looming large on the horizon is improved understanding of volcanogenic tsunamis, particularly in light of recent events that have taken place in the Pacific, as well as recent unrest in American Samoa underneath the island of Ta'u. Of course, during a crisis, we present forecast scenarios and we issue volcanic activity notices and volcano observatory notices for aviation. We do press releases, we do social media updates and TV and radio interviews, and you can sign up for our volcano notification service by subscription. When it's quiet, we help our emergency responders develop emergency response plans for specific volcanoes. We educate the public on how to live with volcanoes in their midst and how to be more resilient. Part of that is through publication, preparedness partnerships, and mitigation partnerships that involve many partners, including the emergency responders. Lastly, we communicate at several levels in the Volcano Hazards Program to a whole host of critical agencies, critical appropriators in Congress, critical partners in other agencies and our counterparts in other countries. We also publish anywhere from 70 to 100 peer-reviewed publications annually. And I can say that life as a program coordinator in volcano hazards is never boring because you can never neglect communicating with any of the agencies or entities that you see surrounding me in this photo. And I thank you for your attention and the opportunity to speak with you this evening, and I'll leave it at that.
Okay, thank you, Charlie. That was a great talk. There was a bunch of good information there for people. Again, if you want to submit questions to Charlie, please put them in the click on the little question and answer box. And let's see, the first question we have is, how many unmonitored volcanoes are there in the United States?
I'm going to say I'll say there are at least 20 unmonitored volcanoes in Alaska. We've got 52 active volcanoes in Alaska. We've got instruments on 31 of them. So about 20 unmonitored volcanoes in Alaska. The other large segment of unmonitored volcanoes in the U.S. constitute the volcanic fields in the intermountain areas of Utah, Nevada, Arizona, New Mexico, where you might have a volcanic field that has 200 cones in it. And each one of those cones was a one-off activity that never repeated. And it would be economically unfeasible and impossible to maintain, nor would you want to instrument every single one of those cones because there's no guarantee that they'll erupt again. In those cases, what we will have in the future in the next phase of NVEWS implementation is better regional and satellite monitoring of those volcanic fields through regional seismic networks and satellite coverage, namely through interferometric synthetic aperture radar and remote sensing.
Okay, that's good. Let's see. Another question was, how does the USGS get Congress to include volcano threat money in the legislation?
Over the past 10.5 years as program coordinator, I have probably done over 200 Capitol Hill briefings. At each briefing, I underscore the importance of why it is that we must monitor the volcanoes in the U.S. The good thing is that we have congressional champions on both sides of the aisle that are interested in doing things in the name of public safety. And a proactive national volcano early warning system is one of the ways we can make the U.S. more resilient to volcano hazards going forward. And Congress, our appropriators, seem to be listening in that the budget of the program has increased substantially over the past 5 years, and we're now starting to get NVEWS specific appropriations on top of the base funding that the program has received in the past. So our congressional champions are listening. They occur on both sides of the aisle, and we are showing that we can, with the resources that we've been appropriated, do things that actually improve our monitoring capability and our capability to issue forecasts and warnings.
Yeah, I know we had a lot of people that were concerned about when Mauna Loa was erupting, if it was going to take out the
Yes.
the ridge. What is it? The Summit Highway or
Yeah, the Saddle Road.
Saddle Road, right?
Yeah.
Okay.
And fortunately, it behaved well, and the lava flow stopped about 1.5 kilometers shy of the Saddle Road. And most of the activity stayed either at the summit or very, very high up on the volcano.
Right. Okay. Another question is, what volcano are you most concerned about right now?
I think the volcano I'm most concerned about right now is Glacier Peak in Washington. And the reason I say that is because that's a volcano that has erupted explosively several times in the past 11,500 years. And it's got one seismometer on it as the only instrument on it currently. So it's the poster child of a heavily, woefully under-monitored volcano in the US that is very high threat. We're going to do something about that this summer, in that we've finally got the permits to install 4 co-located GPS and seismic instruments on Glacier Peak in the summer of 2023. So we will substantially increase our capability for increased, warning and forecast capability at Glacier Peak, when we've known about this insufficiency since 2005.
Okay. Someone else just wants to comment on all the great information that came out with the recent Mauna Loa eruption. The live feed was great. And I have to agree with them, because I spent a lot of time watching some of the stuff that was going on there.
Yes, and we thank our colleagues at NASA Ames for helping us establish that live feed technology. That was also employed during the 2018 Kilauea eruption response, and it's now that we've got it, we're not going back.
There sounds like a good plan there. Another question is, somebody was asking, didn't quite finish their question, but have other countries implemented this type of modeling?
Yes, namely Colombia and Chile have largely emulated in their national volcano monitoring strategies the NVEWS strategy that we've been proposing since 2005 and implementing since about 2010.
Okay. Another question was personal interest. I didn't hear you mention Mount Lassen in Northern California. Any thoughts about Lassen?
Yes, Lassen is due for a network upgrade as well. As you know, Mount Lassen last erupted in 1914 through 1917. So not that long ago, certainly within historical context. And, it's more built up around Lassen today than it was back in the early, 20th century. So we've got to take that into account, as well as the fact that there's much denser air traffic over Mount Lassen now than there was back in 1917.
Okay. Are there many volcanic threats to the United States globally outside of the Pacific Rim regarding ash or VOG?
Certainly within the Caribbean Basin, activity in the Lesser Antilles volcanoes could pose things difficult for ashfall from a large eruption for the U.S. Virgin Islands or Puerto Rico. and it would have an impact on local air traffic restrictions that might be needed to put in place because ash and jet engines don't mix with good result.
Yeah, there was that volcanic eruption in Iceland that literally shut down Europe for 2 or 3 days.
Actually, it shut down air traffic in Europe for 6 days,
6 days.
and there was about 10 billion euros worth of economic impact from Eyjafjallajökull 2010.
Okay. And so far, the last question in the queue is, what's all the recent buzz about Yellowstone caldera?
We have areas of uplift in Yellowstone caldera, writ large, that show centimeter scale deformation on an annual basis. More importantly, we've had recent hydrothermal explosions in Yellowstone to the tune of about, I'm going to say maybe 15 of them in 2019 and also some in 2018. And what we've got to do is improve the fluid monitoring system in Yellowstone, because in a park that has over 1 million visitors each year, we've got to prevent people from getting injured from hydrothermal explosions that could occur in any of the geyser basins, particularly those where previous hydrothermal explosions of that nature have taken place.
Okay. That is so far all the questions in the queue. If somebody wants to send us a question here in the next minute or so, we'll take them. But if not, we may be wrapping this up. I'll give people about 30 seconds to type something in if they want to.
Again, thank you for your attention. Thank you for your questions. I've enjoyed answering them, and please do visit the resource links that are provided. You will find much material of interest, and it will be very informative for you.
Okay, not seeing any more questions, so we'll thank you again, Charlie, for your talk tonight and answering the questions from our audience.
Thank
We'll
you.
also thank all of you for joining us tonight. This lecture will be available in about a week for on-demand viewing at our website at www.usgs.gov/PLS. You can also see many of our previous recordings on that website under the multimedia sections for videos, including a very good one we did last year on Alaskan volcanoes and one from 2021 on Yellowstone. If you would like to subscribe to be a part of our monthly mailing list and receive notifications on these lectures, please feel free to send us an email at wmcesic@usgs.gov, and we will happily add you to our link. Add you to the list. Next month's public lecture will be on February 23rd, which is a Thursday again, at 6 p.m. Pacific time. The speaker will be Kimberly Miller, USGS Wildlife Health Center, and she will be talking about wildlife health science and how it benefits animals, humans, and the environment. Hope to see you then. Goodbye.
Good night.